Welcome to a video on using a polynomial to approximate a function. The goal of the video is to determine a Taylor polynomial or Maclaurin polynomial to approximate a function. So polynomial functions, such as the one given here, can be evaluated by using basic addition, subtraction, multiplication, division. And this is often very beneficial because many functions, like the ones we see here, cannot be evaluated by these basic operations. So sometimes it's helpful to have a polynomial that can be used to approximate other functions. Let's take a look at an animation to see how this will work. Here we have the function f of x equals e to the x, and we have a tangent line at x equals 0. Remember, a tangent line is a linear approximation to a function at a given point. So this would be a degree 1 polynomial approximation to f of x equals e to the x. And watch what happens as we increase the degree of this polynomial approximation. You can see as the degree increases, it becomes a better and better approximation to the actual function in red. Remember, a degree n polynomial has n minus 1 terms, so the more terms a polynomial has, the better it can conform to any given function. Let's take a look at f of x equals cosine x. And again, watch what happens as the degree of the polynomial approximation increases. It becomes a better and better approximation of the original function. Now let's take a look at how we're going to come up with the formula to create the polynomial approximation. If we take the function f of x equals e to the x and determine the equation of the tangent line at the point 0, 1, here's the equation of a line in point slope form. So if we added y1 to the other side, that would be f of 0. F prime of 0 would represent the slope, and then x sub 1 is the x coordinate of the point of tangency. What I want you to notice is at this point here, the two function values agree, and so do the derivatives at x equals 0. Now if we want to find the degree 2 polynomial approximation, we would have to take the linear approximation and add a quadratic term. In order to find this degree 2 polynomial approximation, the function values would have to agree, the first derivatives would have to agree, and now so would the second derivatives at x equals 0. So we could solve for a sub 2 using this condition here if we needed to. And this pattern will continue. If we want to find the degree 3 polynomial approximation, we take the degree 2 polynomial approximation and add a degree 3 term, and we could determine a sub 3 by satisfying the equation where the third derivatives were equal to each other. If we keep doing this, a pattern develops which leads to the formula for a Taylor polynomial. So this states here that if we want the degree n polynomial approximation to a given function, this would be the given formula. What I want you to notice here is that for the degree 1 part of the polynomial, we need the value of the first derivative wherever the polynomial is centered. Meaning in the last example we had it centered at x equals 0, but we can center these at any value of x. For the degree 2 part of the polynomial, we're going to have the value of the second derivative evaluated at c divided by 2 factorial, and so on, all the way out to the degree n part of the polynomial, where we have the nth derivative evaluated at c divided by n factorial. And this is called the nth degree Taylor polynomial for f of x at any given value of c. And if c happens to equal 0, we can call this a Maclaurin polynomial. Let's go and take a look at a couple examples of how this works. So for this problem, we want to determine the 5th degree Taylor polynomial centered at x equals 0 for the given function. Well, we could have called this a Maclaurin polynomial since it is centered at x equals 0. Let's go ahead and see if we can write out the formula for the degree 5 Taylor polynomial. If we want the degree 5 Taylor polynomial, we will have to go out to the 5th derivative of the given function, and then we'll have to divide by 5 factorial. So we're going to have f of 0 plus f prime of 0 times x minus c, but again c is 0, so we'll have times x plus the second derivative evaluated at 0 divided by 2 factorial times x minus 0 squared, or just x squared, plus now we'll have the third derivative evaluated at 0 divided by 3 factorial times x to the third plus the fourth derivative evaluated at 0 divided by 4 factorial times x to the fourth, and then finally plus the fifth derivative evaluated at 0 divided by 5 factorial times x to the fifth. So now let's go ahead and find the first 5 derivatives and then evaluate them at x equals 0. So f prime of x would equal negative sine x. F double prime of x is going to equal negative cosine x. Let's go ahead and find the third derivative over here. The derivative of negative cosine x would be positive sine x. And the fourth derivative would be equal to cosine x. And the fifth derivative would be equal to negative sine x. Now again, we have to evaluate all of these at x equals 0. So f of 0, the cosine of 0 is 1. F prime of 0, well, sine of 0 would be 0, so this would be 0. F double prime of 0, this would be negative 1. F triple prime of 0 would be 0. And the fourth derivative at 0 would be 1. And the fifth derivative at 0 would be 0. This is all the information we need to find the Taylor polynomial approximation. So we'll have t sub 5 of x is equal to f of 0, which is 1, plus f prime of 0 times x, well that would be 0 times x, plus f double prime of 0 divided by 2 factorial. That would be negative 1 divided by 2 factorial times x squared, plus, well, the third derivative evaluated at 0 is equal to 0, so we're going to have 0 times x cubed, plus the fourth derivative evaluated at x equals 0 was 1, so we'll have 1 divided by 4 factorial times x to the fourth. And this last term, the fifth derivative evaluated at 0 is 0, so we'll have 0 times x to the fifth. Let's go ahead and simplify this. The degree 5 Taylor polynomial, or Maclaurin polynomial, would be equal to 1. Let's rewrite this as minus 1/2 x squared. This would be 0 plus, and then 4 factorial is 24, so we'd have 1/24 x to the fourth. And since the degree 5 term is 0, this is our Taylor or Maclaurin polynomial. Let's go and take a look at the graph of what we just found. The blue function is the Taylor polynomial, and the red function is the original function. And notice the polynomial is a good approximation as long as we're close to x equals 0. Let's go ahead and try one more. Here we want to determine the fourth degree Taylor polynomial centered at x equals 1 for the given function. So let's go ahead and see if we can write out the formula for our fourth degree Taylor polynomial when x equals 1. So we'll have f of 1 plus f prime of 1 times x minus 1. Notice now the polynomial is centered at x equals 1, so c is equal to 1. Plus the second derivative evaluated at 1 divided by 2 factorial times x minus 1 to the second, plus the third derivative evaluated at 1 divided by 3 factorial times x minus 1 to the third. And then lastly, the fourth derivative evaluated at 1 divided by 4 factorial times x minus 1 to the fourth power. So let's go ahead and determine the first 4 derivatives of the given function. F prime of x would be equal to 1 over x, which remember is equal to x to the power of negative 1. So the second derivative would be equal to negative x to the negative 2, which would be negative 1 over x to the second. The third derivative would be the derivative of this, which would be positive 2 x to the negative 3. And the fourth derivative would be negative 6 x to the negative 4. which would be negative 6 over x to the fourth. Let's go and see if we can find our Taylor polynomial. F of 1 would be natural log 1, that's 0, plus f prime of 1 would be 1 over 1 or 1 times x minus 1 to the first, plus the second derivative evaluated at 1 divided by 2 factorial. Well, if x is 1, this would be negative 1 divided by 2 factorial times x minus 1 to the second now, plus f triple prime of 1 divided by 3 factorial. Well, f triple prime of 1 would be 2 divided by 1 cubed. That would be 2 divided by 3 factorial times x minus 1 to the third, plus the fourth derivative evaluated at x equals 1, and that would be negative 6 divided by 4 factorial times x minus 1 to the fourth power. Let's go ahead and simplify this, and then we'll check it graphically. So here we'll just have x minus 1. This would be negative 1/2, so we'll write minus 1/2 x minus 1 to the second, plus 3 factorial is 6, so 2 6 would be 1/3 x minus 1 to the third, plus 4 factorial is 24, so 6 over 24 would be 1/4. And since it's negative, we'll go ahead and change this to minus 1/4 x minus 1 to the fourth power. So this would be our degree 4 Taylor polynomial. Let's go and look at this one graphically as well. We have our original function in red, and we have our degree 4 Taylor polynomial in blue. So notice that as long as x is close to positive 1, the blue polynomial is a good approximation of the original function in red. Okay, I hope you found this video helpful. Thank you for watching.